Hey everyone, in this video we're going to look at XFLR5 and how we can use XFLR5 to create a wing and analyze the wing, and also come up with the platform such as the Panel D wing. All right. So we're going to take this step by step, just to ensure that everything is working properly. All right. And I urge you to also follow the same steps because, sometimes when you learn the software, it's tricky to know where things fail. Right. So that's why, if you take it, approach it step by step, making sure everything works every step of the way, it'll help you troubleshoot. All right. So what we're going to do is, before we even model the wing in XFLR5, let's start with the airfoil. All right. So let's go to File. Let's do the direct foil design. Right. So this window will actually pop up. Now, in here, you can input your own airfoil. Using the one that you created using the Joukowsky or Common Traps airfoil, or you can actually import a NACA series airfoil, which is already built into XFLR5. All right. So if you go to foil and then you do like NACA foils, right? Right now, I'm going to do a 2412 airfoil. I'm going to divide it into 200 panels. You can see 200 panels. All right. So that's 2412. Click OK. What I'm going to do is also make sure that I can see the airfoil clearly, because you have a black background. Chances are you're probably not going to be able to see it in the video. So what I'm going to do is actually click this like style right here. So I'm going to go to color, and then I'm going to choose white. Um, and then I'm going to make it a little thicker. And then essentially I'm going to add like some markers. So now you can actually see the profile very clearly, right? It's a 2412 airfoil that we're going to work with. And yeah, it's all set. So, this is the airfoil that we're going to use. All right. So now we have an airfoil. Let's go to the Xfoil direct analysis. But before that, again, if you're using multiple airfoils, make sure to include them as well. For example, I can load another airfoil in here, right? I'm going to do NACA foils, and I'm going to do, instead of 2412, let's do like 0012, right? 200, okay. That's 0012. Now I'm still going to change the color a little bit, maybe add like a fluorescent blue or green, right? So right here, so that I can see better. And then again, change the width, add some pointers, okay? So now you can see the 0012 as well, right? So in this stage, load all the airfoils that you want to use, because this will pop up later in the software, okay? So now let's go to foil and let's let's go to file and do the direct foil analysis, right? This window will pop up. The first thing we need to do is define an analysis, right? Because before we analyze the wing, let's make sure the airfoils are working properly and, showing what you expect to show. All right. So let's go to analysis, do the define an analysis. This window will essentially pop up. Right now, I'm going to add, whatever the Reynolds number that you want, you can simulate it, but I'm going to put like about a 10 million Reynolds number here. Right, but I would urge you guys to calculate the actual flight Reynolds number that you want to simulate, and then click OK. Right. So now, you can see that this tab, direct foil analysis tab, is popped up. Now you have to choose the airfoil, right? Do you want 2412 or 0012, right? So the analysis tab is actually active for 0012, but not for 2412, right? So I can go here and, first run the 0012 and then come back and run the 2412 as well, right? So define the analysis, I'm going to click analyze. You can see that it's plotting a nice profile right here, right? 0012. Now what I can do is, go here, change to 2412, go back to analysis, define an analysis. Again, I'm going to simulate this in in the Reynolds number 10 million as well. Click OK, right? So now I'm going to go through the same, do the analysis. Now you can actually see the two airfoils performance curves, right? CL versus alpha, CD versus alpha, right here, which is again pretty cool. And if you actually go here, you can actually see the CP distribution, right? You can also see the pressure distribution on the airfoil. And if you click animate, it'll go through the different angles of attack and show how the pressure is distributed around the airfoil, right? So it's again all cool. You can do this for 0012 as well, right? You can click animate and then it'll go through and show you the CP distribution. All right. So we now know that the airfoil actually works, right? Showing what we expect to see. There's no problems in this stage. So once you know that there's no problem in XFLR5 simulating the CL versus alpha of all of these, performance curves, for an airfoil, you know that, you can proceed to a wing analysis. All right. Now let's do that. Let's go to file, and now let's go to the wing and plane design. All right. So the wing and plane design, sometimes, you will have multiple windows open up. You have you have like 6 different tabs here, right? So this is where you will actually see all the data. We'll take it step by step. So before we even do the analysis, we have to define a plane, or we have to create an airplane, right? So let's go to plane and define a new plane. All right. Now in XFLR5, you can have an elevator, fin, fuselage, the wing, etc. But here we are only interested in the wing, right? So let's let's uncheck the elevator and the fin. Let's have the main wing alone. Now I'm going to label my airplane as like panel D, wing, right? So panel D wing, click save. All right. So now I have I defined a plane, but I haven't actually changed anything in the wing, right? So in order to, design the wing itself, let's go to plane, go to current plane, and then do edit wing. So when you press edit wing, this window will pop up, right? This is where you can actually design your wing any way you want. All right. So again, you can add multiple sections, and you can add as many as sections as you want, design your wing piece by piece. Now we only have 2 sections. Once the first section right here, which is highlighted, is in the root. And then the second section is actually in the tip. All right. So you can see that red dots popping up, right? Or red line. So that's the 2 panels, right? That's what you're defining here. So the root chord is at 0,0. Right now, I can set my Y, to be like 1,000 millimeters, right? That's you can design your wing to any shape, any length you want. So I'm just going to leave it as such, like 1,000 millimeters, and I'm going to change my chord at the root to have the same chord as the tip. So I have 100, right? So I have like 100, or you can do like even 200, right? You can actually see that by changing these values, you're essentially changing your, your chord, right? So now, you have the same chord and root and the tip, but you have a little bit of offset, which actually puts sweep on your airplane. Say if you don't want your sweep, then just come here and set it equal to 0, right? Now you have a rectangular wing right here, right? If you want, you can add a dihedral, but for now, let's just keep it at 0. If you want, you can add a twist. Again, for now, we'll just keep it at 0. Here's where we select the airfoil. Now, what I'm going to do is you can see the 2 airfoils that we simulated, the previous step popping up here, right? So I'm going to put my root chord as 2412, and I'm going to put my tip chord as 0012. All right. Now I can change my color, of the wing. If you press color right here, you can actually see. You can even select textures. As you can see, you have a textured wing, right? So again, you can change the appearance to anything you want. So what I'm going to do is I'm going to put a dark color here so that you can see some of the things, some of the properties pretty clearly. So I'm going to put black. Black. You can not see it very well, but what I'm going to do is if I actually click this panels icon, right here in the panels icon, now you can actually see the wing pretty clearly, right? So this is essentially the wing that we just simulated. right? Now you can see that the number of, you can control the number of panels by using this, like these, like panels, right? Now, you can change the number, but make, if you have a large number of panels, it will take a lot of computational time, all right? So be very mindful of how many panels you put. So I would not go anywhere above 20. All right, so I'm going to put 20 panels, 20 panels, 20 panels, 20 panels. Okay, so I have 20. Again, you can change the distribution any way you want. I would, just keep it as sine and cosine, as whatever it is, because if you put uniform distribution, what happens is that your leading edge and trailing edge may not be resolved clearly. All right, so you can see the wing right here, right? It's a pretty straightforward wing, rectangular wing, nothing too complicated about this, except you have two different airfoils in the root and the tip, right? So again, the wing, the XFLR5 actually like lofts the connection. So therefore, if you actually take a profile in between the root and the tip, you're going to get a blend of 2412 and 0012, right? It's not like you have a 2412 at the root and 0012 at the tip alone. You have this blend, right? That's essentially what XFLR5 does, right? Just like how you use the loft command in SolidWorks, right? So, now we have a wing, right? Now let's actually, let's do the simulation and see how this looks like before we come back here and change the twist and all that. All right. Now we want to make sure the baseline works, right? Before you add, before you add like any crazy, shape or in any high twist. All right. Now let's. I'm going to click save here. Right now, you see nothing is in here because we haven't performed an analysis. Right. Let's go to analysis. Define an analysis. Again, you have like multiple types of analysis you can do, but we're just going to use the fixed speed. I'm going to use like 30 meters per second. We put the wing at 30 meters per second. Now, if we click analysis here, there are multiple types of analysis, right? The popular ones are the lifting line theory and then the 3D panels, right? Let's start with the lifting line theory analysis. You can change the inertia and you can change all of this if you want, but I'm going to leave it as such. I'm going to use the LLT, lifting line theory first. All right. Now let's click save. You can see the plane analysis tab has activated, right? Goes from -10 to +10 in increments of 1 degree, which is fine with me. So I'm going to click analyze, right? So now, it actually quickly performed the analysis. There are data points which are converged, but there are angles of attack which didn't converge, where you're not going to get any data. So just take a quick look at this. Make sure that you have majority of the angles of attack which are converged. All right. So if you're done with that, then close it. So let's look at the first tab right here. This is essentially what you have, right? This is what you see here is plot of the induced angle of attack versus the span of the wing. All right. So what we're going to do is, we're going to see how this induced angle changes the function of alpha, right? Now look at that. That's at 10 degrees. This is at, I can actually come here and click animate as well. You can see that as the angle of attack changes, what's really happening to my induced angle, right? At negative degrees, I'm creating like an induced angle, and positive degrees, I'm creating like a negative induced angle, right? So that's great. If you want to see other variables, just go right click anywhere on this graph, do the current like graph right here. Then you can actually define graph settings, right? So you can see here, you're plotting induced angle versus y, but you can also plot like lift coefficient. So you can see how the lift distribution looks like in here, right? At multiple angles of attack, right? Which is again, pretty cool. Right now, if you want to export this graph to be plotted in MATLAB or Excel, just do the export graph, it'll actually export all of these, right? As a .tx. I think it may export as a .csv file, but you can upload, you can open .csv file in Excel or MATLAB. All right. So this is pretty great. Now, if we actually go here, You don't see any graph, CL versus alpha, CD versus alpha, and anything for the lifting line theory. I think it's predominantly because the LLT really, is all about getting the distribution for a given platform, right? So, that's what you see here. However, if you click this airplane icon right here, this airplane icon, you would actually get a distribution. So let me uncheck this, right? Um, now you don't see anything in here because you haven't, the airplane color that we specified was black, right? So what I'm going to do is, click panels. Now you can actually see the airplane, right? And you can click surfaces, right? Now this is the wing that we modeled, right? Now what I can do is actually come here and click lift, right? If I click lift, I can actually see the lift distribution on the wing. And the cool thing is I can animate it, and I can see how the lift actually changes as a function of angle of attack, right? Which is pretty cool. You can see the wing changing the alpha as well, right? If I want to look at the induced drag, right, I click this induced drag, I can see the induced drag profile, right? Now, the induced drag is higher at the wingtip because of the formation of the wingtip vortices, right? That's exactly what you expect. And as you change the angle of attack, right, you're creating more and more lift. So, you will have a stronger vortices, which will have higher, like an induced angle, induced drag at the tip, right? So that's essentially what you're seeing. And what you can also do is actually click downwash, right? If you click the downwash, you can see that the downwash profile in the red curve, right? Which is again pretty cool. At positive angles of attack, as you can see, right? Because of the vortices, you have a huge downwash near the wingtip, and it reduces as you move towards the root of the wing, right? Again, due to the span changing, right? The distance from the vortex changes, they'll have a less influence. So, you have a less downwash at the tip, right? So again, it's pretty cool that you were able to see this. And you can plot for different angles of attack in any angles of attack that you want, right? Um, right. So again, this actually works, right? So now what we can do is go back to our plane. Right now, we can actually start adding twists. All right. So if we go back to plane, again, I'm going to put my root chord at about like maybe 8 degrees, and then my tip chord as about -2 degrees. All right. Now, this is just a distribution. Again, this is just to get that high geometric distributions that they use on Pranal D aircraft. All right. So let's go click save. Again, you're not going to see any curves here because you haven't performed the analysis. However, if you look at the side view, you can actually see the twist that you included, right? The root is at a high angles of attack when compared to the wingtip, which is exactly what they have on Pranal D. Right now, if you want the exact specifications of Pranal D, you can go search online and have it programmed have it modeled in in the XFLR5. But for now, we're just gonna go with this an arbitrary twist distribution. Right. Now let's go back here again. Go to analysis. Fixed wing, 30 meters per second, LLT. That's all right. Click save. I'm going to create another file called twist. Click OK. Now let's perform the analysis. Now you can see here again that some of the values are not converged, which is fine as long as you have more angles of attack which are converged. You'll still be able to see the data. All right. So now you can actually see the variations in the lift distribution, the induced drag, and downwash. Let me put at 0 degrees. So I have 0 degrees right here. Right. Now you can see that when compared to a no twist distribution, the lift distribution looks a little different. Like, it looks a little bit more like a bell-shaped lift distribution than anything else. One other thing also to note is that we want is, let me go back to the back view here, right? Now, if you look at the downwash distribution, what you see here are arrows pointing up, right? So that's actually an upwash, right? You can actually get the upwash distribution. Now, this upwash is responsible for induced thrust, which actually gives you a proverse yaw, right, which makes the airplane yaw in the right direction as it roll, right? This is essentially what the panel D does, and this is exactly what we wanted to see, right? So again, you can see that it's the positive upwash direction, which is actually pretty cool. Now, you can look at that in the induced angle as well. So there is a small portion of the induced drag which goes positive, which tells you there is an induced positive induced drag, which is actually the induced thrust. All right. So you can actually see that pretty clearly, in this plot right here. If you click on this, you can see the CL versus the span distribution. And again, I can go back and change. Now I want to look at my induced drag coefficient. Click OK. So you can actually see that there is a portion along the wingtip where you have a negative, like induced drag. Negative drag is simply thrust, right? So negative induced drag, so that means that's a positive induced thrust, which makes the airplane yaw in the right direction of the roll, right? This is, again, pretty cool how it works. Right? And you can do several analysis, look at multiple angles of attack, right? I would urge you to look at multiple parameters so that you have a good understanding of what's going on, right? So you can look at the induced angle, right? You can see the high positive induced angle at the tip, right? Now that changes as a function of angle of attack, but you get these induced thrust at low angles of attack, which is essentially how you cruise, right? So this is pretty cool. Now, before we end this video, I do want to point you guys towards the different analysis tab called 3D panels, because this will allow you to get the CP distribution on the wing. All right. Now let's go to check. Let's click the 3D panels. Let's uncheck the viscous, because viscous simulation is a lot messier and probably you're not gonna get a good convergence, right? So let's stick with the inviscid analysis. Let's click 3D panels, uncheck viscous, and click save. All right. Now again, we need to define the analysis because we just defined the 3D panels, right? Uncheck viscous, that's good. So yeah, this is the panel inviscid, which is what we need. Click OK. All right. So let's once again simulate from -10 to 10 and increments of 1. Click Analyze. Right. Now, this may take some time, right? So the more number of panels you have, the higher the computational time will be. All right. So you can see that, in this case, in 3D panels, most of the angles of attack are converged, right? Which is, again, pretty cool. However, one really interesting aspect of the 3D panel analysis is that it will give you a CP distribution on the wing, right? I'm going to uncheck the lift induced drag and all that. Look at that. That's my CP distribution. Now, you all should know by now what a CP is, coefficient of pressure is, right? It tells you how the velocity is actually changing across the wing when compared to the free stream, and thereby giving you an idea what the pressure is doing, right? Now, if I animate it, right, you can see how the pressure distribution looks like across your wingspan, right, as you change the angle of attack, which again is actually pretty cool. Right now, you can superimpose the lift distribution on top. You can have the induced drag distribution. You can see that there's a certain induced thrust you're getting, and you can actually have the downwash as well. Now you can actually see the upwash along the wingtip, right? So if you animate it, you can see how that changes as a function of span, and make sure that you have the good connection, between what's going on, the downwash, the lift, and the induced drag, right? So this is, in fact, pretty cool, to see, right? And if at multiple angles of attack. So another cool thing that you can also do is, I'm going to put the airplane the wing at 0 degrees, right? You have the induced thrust. You see the upwash on the wingtip. Now, actually, I'm going to click stream. So that will allow me to see the flow lines behind the airfoil, behind the wing, right? So again, let me look at the back view right here. So you can see that, there are roll up of small vortices. Let me uncheck all of these, right? Right now, because of the down upwash, you can see the vortices are rolling up. You can see the the curvature right here, right? You can see the stream, it's curving, right? So essentially, this shows you the wing vortex instead of the wingtip vortex that you have on a regular airplane, right? So in this configuration, you don't have a wingtip vortex, you have a wing vortex, right? Now, as you keep increasing the angle of attack, that wing vortex is going to move towards the tip right here, right? Again, it's pretty cool that that in panel D, at low angles of attack, you don't have a wingtip vortex, you have a wing vortex, right? Which is again, really cool. Let me show you the platform view as well, or the isometric view. So again, you don't see that wingtip vortex, even though if you look at the lift CL, the wing is producing a CL of 0.4, and you don't see the vortex, right? You see the wing vortex in here. But as you keep increasing the angle of attack, now you see a clear rotation of the vortex, right? Which is again the really cool aspect. It's really cool that you can actually see this. You can see the roll up of the vortices and make strong connections between the different aspects of finite wing, right? Finite wing is a lot more interesting than airfoil because you have a distribution and you can do a lot of cool things, right? Now we have different airfoils, we have different twist distributions, and all of that will give you a different performance. And that kind of comes back to the art of wing design, right? You can essentially get any shape you want on any force distribution, sail distribution you want on top of a wing by changing the twist. Now, this is all implicit, right? I mean, if you turn on viscous analysis, there may be some separations going on. We're not accounting for that. But even from a pure understanding standpoint, I think this is a pretty good tool for allow you to visualize what's really happening and the relationship between all of these different parameters. That's very important in a wing, in a finite wing. All right. Hope you enjoyed this video. Hope this kind of gives you a good idea of what to do with XFLR5 and how you can simulate the wing model and extract parameters. Right. So another thing before we leave is that when the 3D panel analysis will also give you a nice CL versus alpha curve, CD versus alpha curve, and all that. So you know what the overall net CL and CD and everything is at a given angle of attack. All right. So hope you enjoyed this video. Hope you use XFLR5 in your future and understand the aerodynamics of finite wings. All right. Bye.